Hello everyone, my name is Xiaoyu Ji. I'm from University of Pittsburgh. Today, I'm presenting our recent paper called Unsupporting Scalable Active Learning-Based Interactive Data Exploration with Uncertainty Estimation Index. Search and data exploration are central to our daily interaction with data, ranging from rudimentary tasks such as online shopping to more complex ones such as retail analysis. With the rapid growth of complexity and volume of available data, the traditional search methods relying on explicit keywords or queries can quickly lose their effectiveness. Furthermore, the user may not be familiar with the underlying search query syntax or data schema, which makes the exploration even more difficult. Such challenges apply to a variety of different fields, including but not limited to scientific computing, financial analysis, and as well as daily search in general. To overcome this challenge in recent years, semi-automated data exploration have drawn a lot of attention in both industrial and academia, as it helps the user to perform more efficient data exploration by providing automated data formulation and semi-automated query adjustments based on some simple feedbacks of the user. One popular way to perform semi-automated data exploration is by leveraging active learning techniques, such that for active learning-based data exploration, users are expected to iteratively provide simple binary feedback for each presented example, and the underlying active learning-based exploration engine will effectively guide the exploration system in training a predictive model that captures the set of objects that are relevant to the user's exploration through the set of most beneficial examples identified by the active learning technique. However, in order to achieve the desired interactiveness, current active learning-based data exploration systems assumes all data fits in main memory. Clearly, such assumption severely hinders the scalability of the systems. In this work, our goal is to design an indexing schema that's specifically tailored for the active learning-based data exploration and in turn enable efficient and scalable data exploration that extends to any data size. Before we move on to our proposed solution, we would like to discuss a popular active learning technique called uncertainty sampling. It is by far the most widely used active learning technique for data exploration due to its efficiency. Essentially, uncertainty sampling is a way to measure the contribution of each data instance in training a predictive model given its current state. It does so by choosing the data point that closest to the current decision boundary, since such data point will be most difficult or uncertain for the current predictive model to classify. And if labels of those data points are obtained, they are expected to boost the exploration accuracy the most. So in this work, we are proposing UEI, the Uncertainty Estimation Index, which is designed specifically for uncertainty sampling. It combines hierarchical in-memory indexing with columnar store and achieves scalability by intelligently managing the in-memory cache. To explain how UEI works, let's start with a two-dimensional space for the illustration purpose. UEI begins by dividing the entire data space into a set of equilateral grids. In the center of each grid, UEI creates one symbolic indexing point that represents the center of the grid. Each symbolic indexing point serves as a pointer that points to the set of actual data on disk that the corresponding grid is representing. While iteratively exploring the space, UEI leverages the predictive model to estimate the uncertainty of each symbolic indexing point and locate the most uncertain one. Now, one popular assumption that UEI is based on is the continuity assumption, such that points that are close to each other are more likely to share a label. Therefore, under the assumption of continuity, it can generally be assumed that the space represented by the most uncertain indexing points should also be relatively more uncertain than the rest of the regions. Therefore, UEI will load and manage in memory the region that found to be most uncertain by the current predictive model. This helps to ensure the exploration can be performed in memory with a set of objects that are highly uncertain to the current predictive model. On the disk, in order to support efficient loading and aggregation of the data, UEI first vertically decomposes the data based on the data attributes. Then it creates an inverted index for each attribute before storing them into separate chunks on the disk. Such approach helps UEI to efficiently load and aggregate data in linear time with the help of a hash table. For the experiment, we use a large real-world dataset called Solon Digit Sky Survey. And we have conducted all of our experiments on an Intel Core i9 machine with 128 gigabytes of mean memory, and we implemented everything with Python 3.7. As a base semi-automated active learning-based data exploration system, we have leveraged request, which was previously published in IEEE Big Data. To model the different complexity in user queries, we have created different relevant region sizes that range from small to large, with the large representing about 2% of the cardinalities and small represents about 0.5% of the cardinality of the entire space. And for the matrices, we have used both user effort in terms of the number of examples that are presented to the user and the response time in terms of milliseconds. And the goal for the exploration is to find the set of objects that maximize the F measure, which is essentially the harmonic means between the precision and recall. Here, we compare the amount of user efforts, in other words, the number of feedback that the user provides between UEI and the base case that performs an exhaustive search over all data objects stored on disk with an MySQL database, which in theory, this base case will lead to a near optimal performance in reducing the number of user feedbacks. From this set of experiments, we can see that in early stage of the exploration, UEI requires notably more samples than the base near optimal case, which is expected as UEI leverages the uncertainty of the predictive model for both the sample selection and the memory management, therefore suffers more from the inaccurate predictive model. However, in later stage of the exploration, to achieve an accuracy of 80 to 90% in capturing all relevant data objects, UEI catches up quickly to the base near optimal model and requires only slightly more samples than the baseline solution. Now, where things get interesting is in the response time. Here we measure the average response time of UEI and base case per each iterations across all experiments for each relevant region sizes. Here, compared to the exhaustive search-based solutions, the UEI achieves 50 times faster response time, which helps the exploration system to achieve the desired interactiveness when exploring large datasets. To conclude, UEI is a novel indexing for active learning-based exploration system. UEI helps data exploration to scale beyond mean memory restrictions. And although UEI is designed for interactive data exploration, however, due to its nature, UEI can also be applied to other active learning-based human-in-the-loop systems as well. And as long as that system leverages active learning and has a requirement for the interactiveness, then the UEI can be applied to help achieve that goal in those systems as well. Thank you so much for attending our presentation. We want to thank NIH for partially supporting this project, and we are ready to take any questions now.